All right, I think we are good to go. We can maybe get started. Let me just make sure that everything is given the green light. Looks solid. All right. So yesterday we started on the Microcorruption wargame, which is a hacking CTF. And we did a handful of these challenges. Basically, the way that it works is each one of these is a different device. They're all based on this like lock thing that is connected via Bluetooth, and you have to provide some input to get it to unlock the door through hacking it. We did a little bit of reverse engineering, did a little bit of Stack Overflow stuff, and that kind of gave us an idea of what to expect. I'm guessing it's going to get at least a bit harder today. All of the devices are based on MSP430s, which is an embedded architecture made by TI. It's pretty simple. There's not that many instructions, so it's pretty easy to pick up for probably anyone looking at this. I think I said yesterday, like I've tried playing this a few times before, and I got like various levels in, and then I would stop playing and never finish it. So I'm hoping to finish it this time. I think there's like 19 or 20 levels, and so we're in like 1, 2, 3, 4, 5, 6 levels in. So we're like a third of the way almost. We can look at Whitehorse or Johannesburg. I forget what the main differences here were. Let me go back to this so it renders properly. So this uses HSM2. Talked about yesterday with HSM is a hardware security module. This is like a physical chip or device that's attached to it that does all the crypto stuff. It's going to hold the key material and make it so that you can't just like pull the keys out of the firmware like we did in some of the early levels. We haven't touched HSM2 yet. This might still use HSM1. Maybe it's worth just going through and doing all the HSM1 stuff and then moving on to HSM2. So the first one the last one we did, the HSM1, it had a Stack Overflow where we were able to overflow the stack and overwrite the return address. So returned out of it, we were able to get control flow. We just called the unlock function. It looks like that might be broken here. I think we saw this yesterday. We looked at it briefly, and I saw that there was a string copy. Let's see if we can go find that again. Yeah, so there's a stir copy here. Let's see where this is getting called. So we have the login function. This is like where our code is running, and it's going to get a string, and it looks like it's going to write the string to here to address 2400 hex, and then it's going to move the stack pointer into R15, and it's going to call stir copy. So I'm not sure where it's copying to, but it's so interesting. So they're not using pushes anymore. They're using these moves. I wonder if the calling convention has changed. Huh. I don't know. Ultimately, what we want to do is we want to get this called, I think. Is this unlock door, or we want to jump back to here, something like that. So I think we'll figure out what the stir copy is doing. I'm gonna set a breakpoint here, and we can look at the memory. So hit reset, continue, and it's gonna prompt us. I'm just gonna do a. So let's finish. All right. So we've broken at the. No, we haven't broken it yet. So I'm gonna hit continue. All right, we've broken up the stir copy. This is our input right here at 2400 hex. Hey, everyone joining. So we have our input right here. Going into stir copy, we can look at the stack. The top of the stack is 43EC. So right here. Then this is like the weird thing is like I don't see anything on the stack. We can look at the implementation of stir copy and see what it's doing. So it's moving R15 into R13 and then jumping to 462C here, and then it's taking what is at the address of R14 and moving it to R12. Moving R12 to what's at the 0th offset of R13. So that's a weird way to write that, but sure. Basically, it's just incrementing the 2 pointers and moving it from one to the other. And then checking to see if R12 is 0. And if it's 0, which means it's the end of the string, then it's going to return. So it looks like the calling convention might have changed, which is, well, I don't know. It's so weird. Like, I mean, we see int right here. Like, it's clearly pushing these values in onto the stack and pulling it from there. We can look at unlock door. And we know that is going to end up passing. So yeah, I mean, this is still doing a push. It's pushing the 7F and then calling the interrupt handler. So that's just so strange. So let's step. We can see right here that it's copying this data. We can assume that down here is going to be like where the return address is. I think this the 443C is actually it. So 443. Yeah, so it's right here. This call is in main, and this is what calls login, and so that's what starts the call stack. It's like right below us, and so the next instruction after that is going to be this. So this right here is what we have to overwrite. So it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So we need 18 characters and then our return address. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Well, you know what? We can't even do that. We have to do it as hex. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 18. And then we're going to want to call, where is unlock? unlock door. So 4644. I'm not 100% sure this is gonna work. We have to see. I mean, I guess we could see if we're able to write that much data to do the copy. I think that we. I mean, it's doing 3F. 3F should be more than enough to read. Let's just do reset. Do that, hex encode it. So that didn't work. We did overwrite it though. Did I put it in backwards? Four 40. Let's step through this. So let's see. There we are, our stack pointer. So we're almost there. I should figure out how many instructions we actually have to do, so we can just skip all this. All right. So that's fine. Step, jump 0. Right. Finish. Compare 1E with what's at 11 bytes from the stack pointer. Oh shit, I'm sorry. I never switched it over. Yep, there we go. Sorry about that. I guess that wasn't super interesting or helpful whatsoever. So let's see here. Stack pointer is 43 EC. So it's gonna look at so 11 bytes would be 1, 2, 3. Oh, hex 11. So it's 16, 17 bytes. It's 1E, which 1E is... So 30. So let's just do this the real easy way. So 4, 3 EC plus 4408. So jumps to login what is it, 458C. So if this is equal, it does that. This is just a length check then. Did we see one? We did 3F up here. What's 1E? 1E is... it's 30. Wait. So 43FD. FF, FE, FD. Right? 43F. So we're comparing it to... why would we compare it to 1E though? Oh, and there's a specific branch there. So basically this is a canary. We can write the value in there. We can write this because we control it. So we're just going to change this from our A's to being 1E's. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And this should basically make this succeed, and then this jump over to here, and then we'll ret into the function. So let's reset this to continue, and we'll do continue. Continue, and yep, there we go. And so this should work. Door unlocked. So we're gonna go for the solve, enter that, and we succeeded. Let's see, where was it? Microcorruption. This was... which one was this? That was Johannesburg. This firmware has a stack flow that occurs due to a stir copy. Which will copy input that is too long over onto the stack. Can be used to overwrite the saved return address from main. Main difference. Exploited in Cusco. another check for the length of the input, which is validated by the code and will branch away from the return address if not valid. We can bypass this because it is stored on the current stack frame before the return address and does not contain any characters that are not permitted by stir copy. All right. Whitehorse, I think, was the HSM 2 one. We're into the 50-point category ones now. Is Santa Cruz also an HSM 2 or is HSM 1? It's still HSM 1. I think the move is to finish all the HSM 1 ones and then move on to HSM 2 and see what else it gives us. Rejects passwords that are too long. We already saw that and bypassed that. All right, so let's see what we got here. So authentication now requires a username and password. We've got stir copy again, another stir copy. There's a good chance that it's just going to be another Stack Overflow of some sort. So this is that same kind of branch again. We're probably going to want to jump over this. Let's just see what we enter here. It looks like we can read in 63 hex bytes for our username. Could be an adjacent memory overflow. So the username and password might be next to each other in memory. And because we can overwrite the null byte, we can basically turn what was 2 buffers into one really long one, and then when the second stir copy runs, it copies like the whole thing. We'll play around a little bit. Let's see what we can see. But where's the actual check, though? Basically, this is where things are happening. Is 7D. What was 7D? Interrupt 7D will pass a given password to the HSM. Wasn't 7F? Oh, 7F does the unlock. Okay. Oops, that's not what I wanted. So 7F does the unlock. 7D invokes the HSM. Do we see anything on the stack? It looks like a return address. Let's see what it actually is. So the return address should be 4440. So this is the return address right here. Let's reset this. Turn that off. Continue, and BBBB. So, all right, let's see where this is. So our BBBB is right here. Theoretically, we might have access to overwrite this. We can give that a shot. I think this actually is the same amount as it was before. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. All right. No, it actually is more. So we need 1, 2, 3. We need 3 more B's. So that'd be 18, 19, 20, 21. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So assuming the overflow is possible here, that'll put us in the overflow. We're 2 bytes off. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 23. What? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 21, 22, 23. Okay. One, two, three, four. So this should be enough, assuming that the overflow is possible. I'm 1 off still. All right, so yeah, this is where the return address was. We can see why this is happening. So we should see like a branch to stop product X right here. There's one there. There's one there. There's one there. So we're right here. This is where we're getting stopped. It's telling us that our password is invalid length. It's too long. So let's see how we're getting there. Moving this byte into 15. It does a sign extend on 15 and then compares what's in R11. So R11 probably is the length. we reusing the initial buffer? So yeah, it's at 24, 00, 01, 02, 03, 04, 24, 04. So same buffer gets reused. What is this? The fuck is this do nothing? It's another Easter egg. Let's see what this Easter egg is. One 6C invalid password. It's weird that I wish there was like an easy way to do this. Maybe we can do it in VS Code. Like the Vim bindings will work there, maybe. Oh, it does. All right, sweet. What do you mean it's not found? I think it's underscore. Yeah. Yeah, okay. So these are just the strings that they're hiding in there. Nothing super interesting. So it's gonna read hex 63 bytes, and it's gonna write it to there. It moves this back into 15, and it puts, so it's calling puts on that value. Moves into R14, move R4 into R15, and then it ands D6. Why is it doing that? All right. 15. So 44 CC. 44 A2. So it's gonna get filled into there, maybe? So R15 is the destination, and R14 is the source. It hands that off. So copies there to B, and we're gonna finish. Move R11. R11 is 43B5. Okay, so R11 has the address that we wrote to in it. It goes to R15. Move R4, which 43 CC. Wait, what? R4 is 43 CC. So it's FEDC. So that's the return address. So it's for some reason that's in R4. It's moving to R14. It's ending off the, so R14 43B4 increment R14 43B 0 1 2 3 4 5. So we're doing some kind of test here. What? So carry is set, so it's not 0. Is this the branch we want to take? So 4, 5, D8. Four, 5, D, E, D8. Oh, it's looking for where the null byte is. So 0 is set. So it's gonna. R14 has 4, 3, B9. 4, 3, B 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is where the 0 is. So it's gonna move that into R11. And then subbing what is an R15, which B5, so 0, 1, 2, 3, 4, 5. So it's getting the difference, so it's going to figure out how long the string is. So R11 should have 4. Yep, R11 has 4 in it. Then we're going to move R4, which is 4, 3, CC. F, E, D, C. Minus hex 1, 8. Which is, I don't know, 16 plus 8. Uh, 16 plus 8. 24. 24 bytes from there. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So it's like right here. So R15 has X10 or X10. So R15 and R11. So yeah, it's comparing these two values, and if it has to carry, it knows that it's bigger. So we're going to do a jump not carry to here. Otherwise, what's it? 2400. Oh, it just prints it, okay. And then this is like the bad case if we do this. So 4, 5, FA. So yeah, it jumps over this. All 15 and R11. Jump carry. We basically need to overwrite, I think this is where things go to shit. We're gonna fail here. Let's reset this. All right. R4 43cc. FEDC. And so that minus 19. For 3B3. Two, 3. So this 8 right here, I think is going to get loaded into R15. Verify that, which it is. And then we need to compare what's in R11 4. Eleven, 12, 13, 14, 15, 16, 17, 18. So we can try changing that 8, and we can make it something. Oh, you know what? So this is a check to make sure that it's at least 8. We can bypass that. I mean, we don't have to bypass it. We know we're gonna do that. So let's reset. 1, 2, 3, 4, 5, 6, 7, 8. The carry flag is set. So that's great. We're going to test the byte at R4 minus 2C. So R4 is here. Uh, 2C. 43A0 right here. Uh, 4644. So we basically need to make this value non-zero, or we need to still overwrite the return pointer and not have one of our situations here. So yeah, so these are all of the, this is the HSM stuff it just did right now. So we're going to end up jumping over this, so 4644 right here. That's where we're going to end up jumping because we have an invalid password. So we got to figure out how we can do some kind of overwrite. Either we need to get into here, which doesn't seem like we have control to write either of these to there. Because all of our writes are below it, and they're always going to go further down. Or the other thing that we could try doing is affecting the stack pointer, because it seems like it's moving the stack. Well, maybe not helpful. We're checking for our minimums, but are we also checking for the maximums? So do we get both stir copies before we start doing checks? Here's one stir copy right here. Here's the other stir copy. It looks like we do. So if you look at how long this is, so we could change the 8 here to a different value. I don't know if that's going to help us. This is the maximum, I think. So we might be able to just overwrite these and make this like 100 or something. Or FF. So it would be 2, 4, 6, 8, 10, 12, 14, 16, 17. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. We'll leave 8 as our minimum because we don't really care. And then we'll do FF as our maximum. And this will be our username. Let me go back to here and I forget what this is. So that's our stir copy. I think we said it was 2023 before. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. And I kind of think it was 4644, but I'm not 100% sure. So this is going to fail right here. Our test is going to fail. And we're going to jump. Password's not correct. We're going to put this out. Finish. And then we're going to test R4 minus 6. CC, CB, A, 9, 8. 4, 3, C8. 1, 2, 3, 4, 5, 6, 7, 8. So it's checking whether that is 0. I think we need to write the whole thing with the first one. And then we fill in the 0 here. Yeah. So that's going to fail. C8. So we wrote up to here. So we need an extra 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. So an extra 23 plus the return address. One. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 22, 23. And then it's 4, 6, 4, 4. And then our password is going to be, we can just do B's. And we just need to make sure that it ends at C8. So I think it's here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So 0, 1, 2, 3, 4, 5, 6, 7, 8. So right here, this has to be 0. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 19. So we need 19 of these. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 19. And that's it, because the next one is 0. So let's reset this. I don't think that this is too long, and I don't think it has any characters we can't do. Continue. This is our username. Finish. Finish. Continue. Step. Finish. 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 I think we went one too far. Okay. Wait, what the fuck just happened? Did we swap the order? Oh, here it is. Okay. This is where we wanted it to be. I think this is correct. So R4, that should be 4, 3, C8. So C0, C1, C3, C4, C5, C6, C7, C8. 0, 1, 2, 3, 4, 5, 6, 7, 8. So we're going to step zero is not set. R4 minus 6. Oh. It's too many bytes. So it needs to be 2 less. That's an easy enough fix. Let's reset this. Finish. I don't need that. I don't need that breakpoint anymore. I don't need that breakpoint anymore. I don't need that breakpoint anymore. Do want that breakpoint, I think, and we want that breakpoint. Actually, we don't really care about that one either. All right. So if we look at this now, we're going to do this test. Jump 0. So 0 is now set. We're going to jump over that. All of this checks out, and then we're going to ret, and our stack pointer is set right here, so we should ret into there. So I'm just going to continue. Instruction address is unaligned. Did we fuck up? Should be right there. Oh, I didn't put in... No, I did put the address in. Is my Indianness off? I think that's wrong. What just happened? Why is PC 1? 4046, and then oh, 444A is what I actually want to be doing. 4A. I just had the address wrong. I don't know where we were jumping to, but that was not right. Continue. There we go, we got it. So let's solve this. We got it. That was Santa Cruz, I guess. Password. Both allow more input to be read than they allow. They allow for each input the low and high end of what is permitted. Let's read this a little bit. Checks that the input is above the minimum and below the maximum. The values used for these comparisons are stored on the stack between two values we provide are copied, which allows us to overwrite them. The checks are performed after the stir copy is called. By overwriting the values in along with the saved return address, we can use the password to fix up a missing null byte and bypass all checks. When login returns, we can execute unlock door. Cool. Jakarta. Is this HSM 1 or 2? HSM 1 still. How many points is this worth? Is this a 40 point or a 50 point? It's a 40. Was this is 50 though. Why did we unlock an easier one? This update further rejects passwords which are too long. It looks like it's mostly the same idea. To use the HSM. Are we still doing stir copies? It looks like we are. And these are probably just our encoded strings again that it uses, like we've been seeing. I'm not going to bother decoding those. So it looks like the username and password maybe no more than 32 characters together. So it's going to add the two together. We might be able to do the same kind of thing we just did, where we can overwrite that number on the stack. Not sure yet. You check if it's cool outside. Maybe open the window. It's getting pretty warm in here. It's 72. It's probably cooler outside. Yeah, it's definitely cooler outside than it is in here. So, let's see what we got here. It looks like most of the same idea. If it's getting too loud, let me know. There is I'm on a busy street, so a lot of people outside. This is where we actually want to get to. This is after the stir copy. So it looks like they're right next to each other. We don't have a value in between them or anything that is going to be used. I wonder if this 5 right here is the length that it figured out. So this is our total length. That's so weird, though, that it combines them together. We lose the null byte from the username. And then it combines 32, 33 with R15. So it's jumping over that. So test username and password is valid. Let's see what this does. Saves R4. We move the stack pointer into R4. We increment R4, decrement the stack pointer. We move 0 into value. So it looks like R15 and R14 are going into there. None of this looks particularly interesting. Basically, we're always going to have this fail. Oh, no, this is easy. We can overwrite it again with the first, because we're gonna do the. It's gonna look for the first instance of a null byte, which as long as we have one that's less than in there, we should be fine. So where's our A's at? Here. So 0, 1, 2, 3, 4, 5. One, 5 minus 0, 1, 2. 3F 0, 2. So we need 113 bytes. Can we actually do that? Yeah, we can. It's gonna reach 55. So puts 113. And then we need where is unlock? Come on, where's unlock? Unlock door. 4C44. Oh. I think we can basically just do B. And I think that might work. So we'll get the overwrite in the first one, and then it'll be less than 32 bytes. Finish. Move that to R15. So Test byte. What's R15 is 2402. This is doing this stir. Move R15 to R11. Oh. So the only problem is that it's going to figure out where our null byte is, and that's where it's going to So what it's going to end up doing is writing to the end right here, which is what we don't want. We want it to go like in here somewhere, because we've already, we've overwritten this, but we need to get up into here to get like a null byte at like 32 bytes into it. So 4202. Well, let's see here real quick. R11. Wait, we did the stir copy. Where's our B? Where the fuck is our B? We did enter a B, right? Oh, it doesn't happen yet. Okay, so we're checking to see. So R11 is hex 73, which is way too big. So we can only write 33 bytes? 21. Oops. We can only write 33 bytes at a time. Which I don't even know if that would get us. How else can we do this? I mean, basically, we're going to fail this because we are over the limit in even one of these. And so it's going to end up jumping like, oh, and we're going to fail it. And branch there. So we can write at most 33 bytes. So let's try this. I mean, let's. So that's 32. Finish it. I'm gonna finish it, and we're gonna do that. We are here. Oh, fuck. 1, 2, 3, 4, 5, 6, 7. All right. Now it's going to take the length of B. Where's our stack here? Okay. Wait, we did overwrite the. Where was our value? This might be our 32, where it's checking the amount we've written or that we've put in there. Hold up. So I only need 4 more bytes. One, two, three, 4, 4, 6, 4. I don't know if 4, 6 is the right one, but we'll just go with it for right now. Puts it. That's fine. It's like we've overwritten it. We're not able to put a 0 in. Like an extra 0 in. We're gonna do that. Okay, we're at the sub. 2402. And I don't think it's an integer overflow or underflow. Where does R11 come from? R11 is just R11 comes from right here. So there's probably some trick for the thing up there, because we're at a point where we're not able to write the 0 into there. I don't think it's an overflow or underflow. But yeah, I mean, I think it's where's that one off? Like effectively, like this is where like, I don't know what this is. 2402. Oh, 0102. Is R11 gonna be our length? Doesn't look like it touches R11. So whatever is in R11 here is coming from this. It's going to have 2402 in it. It's 2402 minus 1F. I guess we can verify this. 23E3? Let's get you banned. Sorry about that, people. There is some spam on here. Get some more music on. All right. Uh, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 20, 21, 22, 23. So R15 goes into R11, which I don't quite understand why we're doing that, because R11 is going to get blown away in a second. 2412. Oh, it's a sub. So 2412. So R14. Copy. C. Add R11 to R15. 4002. So R11 seems like it has the number of bytes that we've written in it. Maybe we can coerce that into having something different. So it's 2, 4, 6, 8, 10, 12, 14, 16. Then R15 ends up having where we're going to copy 2. R15. I think we want to have this breakpoint right here. Or, well, I'm going to jump to a different one, I think. We'll do Whitehorse or Addis Ababa. So conditional unlock doors, like the new thing. I think 7E is the interrupt we care about. Yep. So it pushes on, it's probably username and password, and then the interrupt. More advanced HSM with the ability to directly trigger unlock. The MCU passes the lock of password, and the HSM will trigger the unlock if the password is valid. By default, the interrupt 7E will pass the given password to the HSM. The lock will be opened if the password entered matches the stored password. The stored password can be reset by detaching the HSM from the lock and attaching it to the Model 2 reset device, also included. So I wonder if we can just end up writing shell code that just directly calls this. Oops. I'm gonna set a breakpoint there. Finish. I mean, I think we can probably do it in straight assembly, just do shell code. I don't really see like easy to use gadgets, unfortunately. But this just doesn't seem really helpful to us. So we're going to want to call this. So we need, just backwards, 12, B0, 4, 5, 32. So that's gonna be a call int, and then we're gonna have to do a push 7 7F. Oh no. So we're gonna have a problem here. We can push FF7F and then do like an and. Or like a shift or something maybe. So put call int where is that? Oh, so maybe it does that. Okay, so we're gonna do that. We're gonna do push. Yeah, so this is our problem. So we have this 0, 0 here. We can do a and I wish we could do a not. So it would be like FF 0, and then what's the opposite of 7? So 7 is 1, 2, 4. It'd be that. So that's so the opposite would be 1, 0, 0, 0, which is just 8. So I'm going to do not R15, push R15, and call. I don't know if this is going to work. There's no not. Inverse function. What do we get? We've got AND, OR, XOR. Any of this is probably fine. So our problem is we can't use AND because we'll still need to have a 0, 0 to mask off the FF in the first byte. We could theoretically use XOR. That. So if we want to turn that into there, we need to have FF 0, 7, FF7F. It looks like we have no null bytes here, so this might work. Yep, paste that. All right. And then let's go back to here and see how much space we have. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I have 16 bytes to use, and we have what? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14. We have 14 here, okay. So let's try this. 14, 41, and then we need to jump back to the stack, which I honestly don't remember where we are on here. I think it's like somewhere finish. So it's 3F our first. Yeah, so 3F. It's so it's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B. So it'll be 3, 0, C. So 3, 0, C, 3, C. Continue. Backwards, okay? Instruction is unaligned. 0, 6, 1F. I guess we could retry this. So it's 3C, 0C. Oh, it is backwards. All right, we solved it. A little bit of shellcode. Wait, what? No, did they change the addresses on this? Oh, nope. 0C, 3C. Alright, there we go. There's probably an easier way to do this, and I'm curious what it is. That was Whitehorse. There is a stack overflow. Login function where it's longer. Stack. Due to the stack being executable, shellcode, lack of ASLR, we can provide shellcode directly on the stack and jump to it. To unlock the lock. Small bytes, then pad it. Is the beginning of our inputs. All right. Cool. I'm curious what the intended solution is, if this was like the easy one or not. Microcorruption, Whitehorse. Okay. Blah, blah, blah. Okay, so yeah, it is building shellcode. Oh. That's interesting. So we don't actually have to worry about the null bytes. We can just do that, I guess. One, 4, 3, 8. So how did they get the jump to work? That's not actually all that interesting, because you still need to leak. I mean, you still need to know the address of 3802, which is the where the address starts. That's fine. So yeah, I guess this actually was like the correct solution. There wasn't something easier, although we didn't have to do this this null byte trickery here to avoid it, but that's fine. We had enough bytes here to do it, and there's no downside to it. It's just extra instructions that run. All right. Well, let's see what else we got here. I think Jakarta was the one that we hadn't solved yet. Montevideo. It's HSM2. I wonder if we can reuse the same attack here. This time it's doing the string copy. Move 64 into R13. What's 64? Is that like D or something? Yeah. Three, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So it's 16 bytes. One, 2, 3, 4, 5, 6, 7, 8. We can still use the same exact shellcode, I think. Here's Montevideo. We just need to update the return address, which would be 43. So it's 2 bytes in, so that's F E E. Four, 3 EE. And I think this will probably just work. Oh, and is our calling address the same? What is the address for it is 4, 5. Four, 5. 4A. Guess it's good we solved it the hard way first. Reset. could be that any number of things are just off. So right here is our return address. Oh. But we can always put it after. We get how many bytes? We get 16 times 3. There should be plenty. We don't need to have these extra bytes here anymore. That's fine. And we're going to start at F043. Um, 16, 1, 2, 3, 4. Three, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So I think that we're okay here. The shellcode should be more or less like the same, and we're just gonna have to put this at the end. Finish. What the fuck? Why? Oh. 4, 4. So 0, 1. So I need a padding byte there. So we just need to like have 2 extra bytes there, so that we still align the instructions. So on a 16-byte boundary, 16-bit boundary, but also we don't use a 0, 0 there, and that's probably fine. Finish, finish. finish. What happened here? Oh, I ended up writing like bad shit here. What is that memset exactly doing? So it's hex 64. It's 100 bytes. I think it's just overwriting this. Realistically, see, all these A's are still here. I don't know if that was a problem. So 1 second. Let's go back to this and make sure I didn't fuck something up. Like, it's really basic. Alright. So 4/4, 3C. So that's all fine. I think we're still okay. Oh, I think we just have this backwards. Or 3. Where's our shellcode at? It's... That's all fine. Yeah, so that's good. Step, step, push R15 4-5 4A 4C. Yeah, our code was fine before. All right, let's solve this. Function. Stack the it's called copy the data as much no encountered don't use shellcode right. It should be fine. We can reuse the same. What is this? Whitehorse. In Whitehorse, address is on the stack. All right. So these are both HSM1 still. Let's see here, really quick. So many people doing these. Give me this. So there's still like 1, 2, 3, 4, 5, 6, 7. 7 that we don't know about. Plus the 2 that we do know. And I guess this is where it starts to get like really hard. Not exactly sure like what changes, but these are pretty far. I mean, like. So I wonder how they got smaller CPU counts. So I guess like, well, let's see. So they get 0 CPU cycles. That's not real. Oh, it says 0. So someone did it in 6. It's interesting. I wonder how much golfing you can do here. So Jakarta should be easier than Addis Ababa. And I guess when we solve like one of them, it's gonna unlock the others. Or maybe we have to solve both in order to get to the 100 pointers. Um, this seems like it might be a little simpler. Um, so we still have an unlock door function that we can call. So we save R4, we move there, so this is just all the setup if we door it. And then we're... Is this HSM 7D is HSM 2, right? What's HSM 1? See if we can figure out like where it's doing a check. Oh. What calls main? Anything? It's this. So this should be our return address. Is 442C. Turn the lights on real quick. So I don't see... Yeah, okay. So I'm pretty sure that this is what calls main. So 442C is what we should be looking for. I don't see anything though. 1 second, got a call coming in. All right, we're back. Sorry about that. I had a phone call. But I think I have to reload this now. Where were we? We're trying to figure out like where our return address is. There should be something on the stack here. Set. Oh. The reason that we don't have a return address. Hey, Bevin. So the reason we don't have a return address here is because we're doing a jump and we're not doing a call. Which is shitty because it means that we're not going to be able to overwrite the return address in main. And that's also interesting. It looks like we don't even... Oh, we fall through. Maybe? Move R5, R15. We'll just do this. It's gonna fall through, which it does right there. So we fell through into main. SP is 366A. Where is the stack pointer? So we have the ability to write here. It looks like we can see where our stir copy is going to get written to. We might be able to overwrite the text section. I don't know if that's writable or not. It doesn't really tell us. All right, we're in A, finish. So we just wrote our A's at 2400. We're gonna copy it over onto the stack. It looks like we can get 16, 17, 18, 19 bytes. So 2400 is going into R15. What's interesting is that I don't actually see it parsing it in any way. Like, it's supposed to have a colon in between. So we move SP 15 to the stack pointer. So this ends up being where it writes the value. R15 is going to have the return address there, or the return value there. R11, 3656. 36.5, 2, 3, 4, 5. The beginning of our string. You know what? I think this is a format string bug. If it's printf. We can verify this. Continue. Continue. Hold up. Let's. Interesting. Okay, so yeah, it is working. We do have a format string. So we probably have the ability to do arbitrary overwrites. We have to figure out what we want to do here with that. So it's going to do the... So this is main. So we have this 451F. Okay. So we could so now if this was like a Linux binary, the way that we would probably do this is we would overwrite the address of printf in the GOT entry to do like system, because we're not on Linux, we don't have like all of that. We don't get to do that. We don't have a GOT entry. We just have like raw data here. I don't know if this is writable. We can look at, we can does printf run before? No, it doesn't. It's this. So this is what we end up wanting to overwrite, is this address. So we need to write non-zero to whatever that is. All right, we're just gonna do that. All right, so we want to overwrite basically this address, and there's a couple ways we can do this. So we have the ability to arbitrarily write. Probably we need to see. So we'll probably have to wrap around the address space. Which, maybe not the end of the world. Let's try something. Percent x, percent x. Let's see which values were 7825. So right here. $100 X. Is it not right? Format. Give me where are we on? So 5036. So 5036 followed by %n. It's been a long time since I've written format string overflow. So I think we're okay, because I think that... whoops, that's not what I wanted. I want... $25, 6E. SP is at 3654. So I think the 6 here is correct. Problem is I don't know what this printf supports. It doesn't seem like it supports the ability to do direct indexing. It does seem like it supports the %n, which will write data. I need just like... So basically what we're going to do is we're going to use this format string so that we can overwrite this value right here with something that's non-zero. Our input, let's see here, is 1, 2, 3, 4. 6p. I wonder if it has to be behind it. I don't remember. It's been so long since I've done one of these. Yeah. I don't know. I think it's time to call it and pick this up maybe sometime this week. I gotta do some more reading and remember exactly how to use the primitives and figure out like what we have access to. I don't know for sure that we can use the %n, but that's kind of like what I'm leaning toward, is that we're gonna overwrite this value right here with it, and then we can just bypass that check. The one right here. Anyway, I'm gonna call it for the night. Hope everyone found this at least somewhat interesting and informative. I'll pick it up later this week. Bye.